In this video, we will present the principles used to size a conductor considering the thermal stresses during a short circuit condition. It is important to note that, according to Section 110.10 of the National Electrical Code and the Mexican Official Standard NOM 001 Std 2012, hereinafter referred to simply as the code, overcurrent protective devices, total impedance, short-circuit interrupting ratings of equipment, and other characteristics of the circuit to be protected, shall be selected and coordinated so that, circuit protective devices operate to clear a fault without causing damage to the electrical equipment in the circuit. This requirement makes it necessary to review all circuit components, among which the conductor itself is one of the most critical elements. To verify whether a conductor is suitable to withstand the thermal stresses produced during a short circuit, the equation included in Table 240-92b of the code, titled Short Circuit Current Rating of Branch Circuit Conductors, is applied. In the past, common engineering practice required verification only for conductors sized 1/0 AWG and larger, as well as medium voltage conductors. This approach was mainly due to the limited accuracy of short circuit studies. Today, however, it is clear that all conductors must be verified in order to comply with the requirements of Section 110.10. Although the software treats short-circuit conductor verification as optional, it is strongly recommended to enter the required data and perform the short-circuit validation for all conductors in the system. The equation in Table 240-92b allows the calculation of the minimum conductor cross-section area required to carry the fault current for the duration of the short circuit. In this calculation, it is assumed that, under initial conditions, the conductor is operating at its normal operating temperature, and that under final conditions the maximum instantaneous temperature rise of the conductor is not exceeded. As shown, the equation includes factors that depend on the conductor material, resulting in different formulas for copper and aluminum conductors. As shown in the data entry window, 4 key parameters are required to verify the conductor against thermal short circuit stresses. The first is the fault current flowing through the conductor, entered in kiloamperes. The second is the fault duration, which may be expressed in cycles or seconds. Finally, the maximum instantaneous temperature rise of the conductor must be considered. When accessing this screen, this value is predefined, as it is determined by the software based on the conductor insulation type, specified in the General Data section for the selected conductor. These values are taken from the standard IEEE 242, which provides typical values for the maximum instantaneous temperature rise for each insulation. However, it is recommended to consult the selected cable manufacturer's data, to validate or directly obtain the specific allowable instantaneous temperature for the conductor. The final field in this window is a checkbox that allows to compute the fault current reduced by considering the effect of the conductor resistance and reactance. This concept is important to avoid unnecessary conductor oversizing. During early stages of a project, a detailed short-circuit study is often not yet available, and therefore the actual fault current value is unknown. In such cases, how can the conductor be verified for thermal stresses? A common practice is to assume the short time withstand rating of the MCC or switchboard, which follows standardized values and represents, in the worst case, the maximum current that could occur in this part of the system. Another option is to use the interrupting rating of the protective device as the maximum fault current flowing through the circuit. While these assumptions ensure the most critical operating condition, they may also lead to costly conductor oversizing. To understand the effect of this checkbox, consider that the conductor must carry the maximum fault current really flowing through it. Let's analyze the maximum current transported by the conductor. Assuming the conductor is continuous end-to-end, there are only 2 possible fault locations. 1.at the terminals of the protective device, or 2.at the load terminals. Faults at intermediate points implicate insulation failure and would require cable replacement, so it is not necessary for the conductor to withstand fault current at those locations. In a typical radial system, fed only from the utility, if the fault occurs at the protective device terminals, the conductor will only carry the contribution current, in the case of motor loads. For other load types, the conductor would carry no current under this fault condition. If the fault occurs at the load terminals, which is the most common case, the fault current will be equal to the bus fault current attenuated by the conductor resistance and reactance. In low-voltage systems with small conductor sizes, this reduction can be significant, reducing fault current from tens of kiloamperes at the bus to only a few kiloamperes at the load. The software assumes an infinite bus analysis and applies a Thevenin equivalent impedance model to determine the reduced fault current at the load end. Details of the formulas used for Thevenin resistance and reactance reduction can be found in the help section by pressing F1. If a detailed short circuit study is available, providing fault current values at both the main bus and the load terminals, and including information on upstream and downstream fault current contributions, the currents flowing through the conductor must be analyzed to determine the maximum fault current to be used for conductor validation. In this case, the maximum fault current value should be entered, and the current reduction checkbox should remain disabled. This condition is typical for radial electrical systems. However, in systems with tie breakers, multiple power sources, utility interconnections, or generators, it becomes critical that the entered fault current represents the maximum current flowing through the conductor under all fault scenarios. In such cases, it is recommended to enter the maximum fault current from the short circuit study and leave the checkbox to decrement the current inactive. If the conductor size previously validated for ampacity and voltage drop is smaller than the size required for short circuit conditions, the software will initiate an iterative process until it finds the combination of conductor size and number of conductors per phase that provides the minimum required cross-sectional area to withstand the short circuit thermal stresses. In the detailed calculation report, the required minimum conductor area and the corresponding iterations used to satisfy the short circuit thermal requirements can be reviewed. These are the basic steps for selecting conductors capable of withstanding thermal stresses during short-circuit conditions using the Sizer Electric software. For detailed information, refer to the user manual under the Help option, or review the help files included in that section. Remember that online help is always available by pressing the F1 key on your keyboard. Thank you for your attention. We also recommend viewing the complimentary videos on conductor selection, cable tray and conduit selection, and grounding grid design for a complete understanding of the Sizer Electric software.